Okay, Honorable Principal Sir of Holy Institute of Technology has joined the session. So I request our co-host Arohini, who will hold the session for today. Arohini is a member of this IEEE MTT-S society as well as the core member of this society, SBC. So Arohini, can you hear me?
Yes, sir.
So you can go ahead with the session.
Okay, sure, sir. So, on behalf of IEEE MTT-S HIV Student Branch Chapter, it is my privilege to welcome you all to today's distinguished lecture on microwave and RF devices and their interactions with novel nanomaterials for sensing and communication applications. So, we are truly honored to have with us all the students, faculty members, and our respected dignitaries, and of course, our distinguished speaker and guest of honor. So before we begin, so allow me to introduce our speaker, Dr. Mohammad Hossein Zarifi, who is an associate professor and Tier 2 principal research chair in sensors and microelectronics at the School of Engineering, University of British Columbia, Canada, where he also directs the Okanagan Microelectronics and Gigahertz Applications Laboratory, which is the Omega Lab. He has authored and co-authored more than 150 peer-reviewed papers and holds 6 patents. His research remains focused on applied electronics, circuits, and systems for communication and sensing applications. Dr. Zarifi has been honored with the Emerging Researcher Award in 2020 and the Best Teaching Award in 2021 at UBC, and he currently holds the position as an IEEE MTT-S Distinguished Microwave Lecturer for the class of 2024-2027. So it is a privilege to host such a highly accomplished academic and researcher today, sir. So to formally commence the proceedings, I would now like to invite our respected principal, sir, Dr. Tarun Kanti Jana, to deliver the inaugural address and share his words of encouragement.
Hello, am I audible?
Yes, sir.
Okay, so good afternoon, ladies and gentlemen, respected, distinguished Professor Dr. Mohammad H. Zarifi, Head of the Department of Electronics and Communications, faculty members, coordinators, student coordinator, researchers, and other participants. IEEE MTT-S HIT Student Branch Chapter, it was, if I am not wrong, it was established in 2025, 31st of January, in the august presence of Dr. Gautam Chattopadhyay, who is a very senior professor in Caltech and also IEEE senior member and NASA JPL member of the NASA JPL laboratories. Since then, this particularly student branch chapter is continuously pursuing different activities to reach to a greater height through different type of activities pertaining to the academia and in its application potentials. Today we are fortunate that Professor Zarifi is with us for an important and extremely relevant lecture session he will be about to deliver on a very contemporary and emerging topic like the titled microwave, RF devices and their interactions with the novel nanomaterials for sensing and communication applications. In fact, I am from a different background and I don't have much ideas about the microwave or the wireless communication systems. But as a common people in the society, this much is visible clearly that in our different walk of present day's modern life, there is a extremely important role played by this microwave and radio frequency communication, such as cellular network, Wi-Fi, Bluetooth, GPS, ATC. So in fact, in that now we are living in the world of communication. So without this microwave and radio frequency communication, the world will come to an halt. So it has got the immense potential, and it has got an application domains in 360 degrees in the communication, in the radar, in the navigation, heating, industry, medical, and many more. And with the increase in the complexities in the business environment, there is an extremely important need of miniaturization of the devices. So in one hand, we have to find out the typical technologies for microwave and radio frequency communications and miniaturization of the devices. Because once we go for the miniaturization, it will come up with a lot of accompanied advantages such as flexibility, less space, compactness, ease of maintenance, and many more. So this today's lecture, I believe, will deliver an opportunity, or will create an opportunity on the platform to discuss the different aspects of radio wave and high frequency communications, and what are the upcoming and emerging materials which could be utilized or which are amenable for developing different your communication devices. I convey my sincere regards and gratitude to the organizer and to Professor Zarifi to kindly consented for delivering his speeches on the different aspects of this microwave and RF devices and their interactions with the novel nanomaterials, so that this particular student branch chapter, along with the other faculty members and researchers, will be tremendously benefited to carry forward their research work and to open up new possibilities which will be extremely beneficial for the mankind and the society as a whole. So without any further wastage of time, I once again convey my sincere regards and thanks to Professor Zarifi and the organizer and all the student member of the IEEE MTT-S HIT SBC, so that and I wish this particular lecture will have immense benefit in our academic and research career to propel ahead it, and this particular student branch chapter will be proliferated in the years to come by organizing or the holding different type of events in the under the banner of IEEE MTTS, so as to justify the credibility of this particular student branch chapter. So I wish all concerned will enjoy a lot and will have an opportunity to interact with Professor Zarifi to clear their doubts, to identify the promising areas and the cutting edge technologies, so as to foster these very promising areas of communication. Thank you very much.
Thank you very much, sir, for shedding some light on the significance of today's subject and for your inspiring words. Next, I invite our respected head of the Department of Electronics and Communication Engineering, Professor Dr. Chanchal Kumar Deb, to address the gathering, sir.
Am I audible?
Yes, sir.
Hello. Am I audible?
Yes, sir, you are audible.
Okay. Good afternoon, everyone, and warm welcome to our respected principal sir, Professor Tarun Kanti Jana, our guest, Professor Mohammad H. Zarifi, and all the faculty members and my dear students. In our department, so we have the three student chapters. So that is IEEE MTT-S Society and IET and the GTG. So these chapters are very much active and they have organized the different type of workshops, seminar, conferences throughout the year. And I am happy to share that our IEEE MTT-S Society student chapter was inaugurated in this year by Gautam Chattopadhyay, the scientist NASA in the JPL laboratories. As you know, the IEEE is the world's largest technical professional organization, and MTTS, that is the Microwave Theory and Technical Society, fostered on the microwaves, RF, antennas, wireless system. Having a student branch chapters of IEEE MTT-S Society in our college bring many advantages. Today, under this chapter, we have a special invited talk by Professor Mohammad H. Zarifi from the University of British Columbia on the topic of microwave engineering. I request all the students to listen carefully and interact with the sir. I am sure this talk will be very much useful for everyone. And last of all, I would like to thank the organizer and the student body of the student. And I would like to thank our guest, Professor Mohammad H. Zarif, for their valuable time. And I would like to thank to all of you. And thank you for all. And next, I will request to our coordinator, Surjit sir, please carry forward your talk. And thank you to all of you.
Thank you, sir, for your kind words. Arohini, please continue.
Yes, sir. Thank you so much, sir, for your valuable words of support. And now, without further delay, it is my honor to invite Dr. Zarifi to deliver his distinguished lecture. And just a side note for all the participants in this lecture, you all are requested to listen attentively and note down any queries or questions you have, if you have any. And you might be able to ask your queries in the chat box itself. At the end, we will be opening a Q&A session. So we request you to keep your doubts ready and type them in the chat box. So thank you, sir. Sir, the virtual stage is all yours.
Okay.
Thank you very much.
Okay, sir, just a minute. Actually, chat box is not available for all. There is a Q&A section inside the Google Meet. So you can put your questions there and we'll ask, we'll share with the speaker, Professor Zarifi, at the end of the talk. Okay, thank you. Sir, please continue.
Absolutely. So thank you, everyone, and thank you very much for attending this session. I would like to say hi and good evening to everyone, and thank you for taking time for attending this maybe late one and very early morning talk for me. It's around 5:30 in BC in Canada. So today I'm going to talk about the microwave and RF devices and their interactions with the novel materials for sensing and communication applications as a part of my IEEE Microwave and MTTS Society Distinguished Lecture Series. Before going forward, I would like to thank all the organizers of this event and the chapter and the students who are enthusiastically involved in this talk and in this event. I also want to mention and acknowledge IEEE Microwave Distinguished Lecture Program for providing this platform for the purpose of presentations and knowledge sharing and establishing a collaborative platforms between different continents, different countries, different students at different places. All right, so now going back to my presentation, before I start about discussing very technical things, I want to introduce and talk a little bit about why we need to become an IEEE MTT-S member. And if you are not an IEEE MTT-S member, I highly encourage you to attend the society today, because you will see that there are lots of advantages that we can gain from this society. So one of the main reason that I believe we have to attend. Oh, I'm not sure why it's not. Oh, yeah. So one of the main reasons that we need to attend and join this society is mainly related to the networking and being able to get introduce ourselves to other people, our peers, and even companies for the purpose of making the careers. I also want at some point in between my talk, I will definitely talk about my personal experience. So it was almost 2013 that for the first time I attended a conference, one of the biggest and the most important IEEE MTT conference. It's called the IMS, International Microwave Symposium. And at that time, I didn't really believe that it's gonna be a career decision for me. I thought that that could be just another conference that I'm attending. But by attending that conference, that entirely changed my direction and my research and even my focus and my vision. So, and I started to make lots of friends at the same level of students, which now they are, to be honest, I was checking on some of my friends and they are very high rank, they have a high rank careers at this moment in their universities, and not only in their universities, but also in the microwave society. And also, I get the chance to get to know other professors or peers that I just used to see their names on the books and on the papers. So that's why I highly recommend, if you can, join this society. And by joining this society, you are opening lots of professional and networking activities to yourself, voluntary activities to yourself, being interacted with other students that they are the future researchers, they are going to be the future leaders, and this is the time to start making these sort of connections. By becoming a member of MTTS, you are also, as a student, you are going to have access to lots of publications. And why this is important? Because most of the technical papers and most of the new advancements in the field are being published in these journals. And having access to these journals will definitely widen your knowledge and definitely help to deepen the knowledge that you are building in any place all around the world. Again, attending conferences is going to be dominant and prominent and promote, because then you will start making connections. So I mentioned a couple of conferences here, and now I think I need to go back and update this slide, because MapCon, which is happening in India, is becoming one of the very good and very attractive conferences in the microwave society, and hopefully this year I will be attending as a speaker, as an invited speaker, and also I will deliver some talks. So I'm looking forward to see you in person if you are also attending MapCon this year. So by this, definitely you can have access to award and scholarships. So our society also sometimes, and most of the time, provide student scholarships, travel grants, travel awards, and even sometimes for the undergrad and grad students. So depending on the type of the program, you can have access to these kind of awards, and you can apply. And if you are being selected, that's a good kind of support to attend conferences and events in this level. At the end, I just want to mention that this is a community for engineering, and it is welcomed by everyone, regardless of the race, regardless of the racial. We are just engineers. We want to work together closely to make the future safe and sound for the human being. And at the end, the good thing about the engineers are, if there's a no way, we will build a way. So that's why we are here. Okay, so with that, I just want to now get more to the technical discussions. And today I decided to present about our very recent activities in my lab, which is also related to the novel materials and sensors and communication aspect. So in today's talk, I'm going to talk about why RF and microwave sensors, why not other type of sensors. And then I'll discuss about very briefly on integration of these microwave sensors with artificial algorithms, and then how these new techniques and methods are being able to be evolved by using augmented reality. And then we will talk about microwave novel materials interaction and why we need that interaction. And from there, I will introduce the recent research, which is based on MXene, one of the recently discovered materials. And then you will see lots of very interesting things that can happen using this MXene material. I will conclude my talk by acknowledgement and wrapping up with the question and answers. So first question that comes to mind is why we need RF and microwave sensors? Why not other type of sensors? So as a person that's working at different frequency bands, and I can give you a very briefly that when I got my PhD on brain-computer interface, and at that application, the frequency band or frequency operational frequencies from, let's say, millihertz to a couple of kilohertz, and that's it. And then I moved to University of Alberta, and then at that university I was doing more MEMS structures, which are very good devices, but at the same time fragile and cannot survive in harsh environments like in oil and gas environment, or very vibrant environment, or very a cold environment such as north of Canada, or maybe very hot environment sometime all around the world, and in the deserts or so on. So then we started to think about, okay, can we use a method that it's not, let's say, being contaminated by the material under test, and at the same time, it's not contaminating the environment. So right away, this question brings us to the non-contact and wireless method of detection. And as soon as we come to the wireless and non-contact detection, first things that comes to mind is microwave. So this microwave can provide us high sensitivity and accuracy. Also, the measurement is real time because wave is interacting with materials in a real time manner. And not only it does the sensing, but also because of its external and internal kind of capability, the wireless communication freely comes with that. So that means that if we have a sensor, we don't need to add an extra wireless device. These two can be accumulated in one single device. And also, it's compliance with safe and health applications and less legal complications. And less legal complications, I can refer to the cameras. As an example, in the airports and any other places that they are using cameras for surveillances, they have to avoid any legal complications, they also need to put a sign saying that there is a camera in place. But for microwave, because microwave doesn't gather any personal and individual informations, so that that kind of legal complications are already avoided. The next slide is mainly talking about combining the microwave sensors and artificial algorithms with these new developments that's happening. So one of the things that I can easily mention is microwave devices are compatible with the data processing and especially with the new techniques that AI is providing for us. So previously, I remember that in order to interpret the S21 data, a person or an individual needs to understand the concept of S parameters, reflection, transmission, and gammas, and impedance matching, and so on and so forth. But with the help of AI, all these things has been removed, and now AI can do the processing of data and give us whether it's go or no go, or detected or not detected. So that means that combination of AI and microwave systems are also simple and easier than any other methods. This is the photo of one of the chips. Let me see if I can have my presentation. I'm not sure. Can you see my mouse on the? Yeah, I think the mouse is visible. So yeah, so this is actually one of the chips that we built in my lab for that we implemented artificial neural network on a chip at 22 nanometer technology. So this can be easily integrated with the microwave devices, and that helps us to go towards edge device application. And if you are not familiar with the edge devices are the devices that they have sensing and processing at the same unit, at the same place. So that reduces our dependency to the network. That reduces our dependency to the availability of the network when in the case that we don't have internet or connection or network available to the sensor. I also want to mention that this is actually one of the research that was done by my student Vishal Balasubramanian, and he's also now become a young professional speaker. So I highly recommend, if you want, you can invite him for the talk as well. But this is the work that he has done as a part of his PhD. So this is RF and microwave sensors integrated with the augmented reality. Again, going back to the interpretation of the data, previously we need to measure S11, S21, extract resonant frequency, resonant amplitude. But as you can see in an application like this, which we used for monitoring the thickness or integrity of a coding, as you can see, everything goes to the cloud, the processing has been done in the cloud, and then comes back down to the phone. And in your phone, you just point it towards the surface that you are interested, and it says that, okay, the coding is intact, or the coding has been removed or absent, and then you need to redo the coding. So that means the processing and analyzing the data could be as simple as seeing the change in a color on your phone. But we demonstrate all these applications and all these beautiful things that can be done using microwave. But the question is how these things are being happening. And in order to answer that, we need to go back to the basic. And basically, I really love this RLC circuit. And even after, I don't know, 20 years of my career at university, still when I'm looking back to this circuit, there are lots of things that I don't understand. I'm trying to understand and explain. So one of the beautiful things about this RLC circuit, that if you extract the impedance or admittance, you see something like a bell-shaped curve. And this bell-shaped curve is called, a resonant profile. So in this resonant profile, a couple of things are important. One is resonant frequency, and the other one is resonant amplitude. And resonant frequency is the frequency correlated to the amplitude with the maximum amplitude of this curve. So if you write the math and do a little bit of simple math application, you will find out that omega r can be related. So if you have two plates in parallel with each other, you can find out that omega r, which is the resonant frequency, can be related to the loss of the material in between these two parallel plates of the capacitance and the dielectric properties of the material in between those two parallel plate capacitance. Also, you can find out there is a relation between the resonant amplitude with those parameters, as you can see here in these two equations. So if we change that, which means that if we introduce a material or change a material, or a material changes because of presence of something, and this curve moves, then we can detect variations in permittivity in omega r and AR. And then lots of interesting things happens, and these are samples of the devices that I or my students made in my lab, and they tested and reported in different papers. So that means, okay, we understood that now we need to work with materials and then monitor their changes. And if we do that, these are the figures and the TOC, table of contents, from different papers that published by my students. So you can see that we use microwave for gas sensing, we use microwave directly for light detection, we use microwave for hazardous gas detection and monitoring and using it as a smart PPE. But how these interesting things are happening? So we need an interface layer, because microwave devices by themselves, they are insensitive to variations of the gases, or let's say temperature, or let's say humidity. And then I'm telling that it's insensitive to temperature and humidity and so on. I'm referring to very small changes and decent range of operation. Yes, definitely, if you burn something or bring it to 2000 degrees Celsius, definitely something happens and you might not have the device. But what I'm referring to is more like a reasonable range of operation. So, and this is obvious because you don't want your cell phone to behave differently or change the quality of the sound or communication when you are standing in shadow or you are standing under the sun close to the beach. So, in order to make these devices sensitive, as you can see, we investigated different materials. So these are the materials that we have recently or previously investigated in my lab. One of the materials is titanium dioxide, TiO2, and there is a IEEE MTT-S featured webinar by myself. If you are interested, you can go and watch it. Here is the link for it. We also work on reduced graphene oxide, RGOs, and conductive polymers such as P.PSS, non-conductive polymers such as PDMS, and also we work with recently laser-induced graphene oxide. This is something also very interesting. We published a paper in TMTT. If you are interested, you can take a look. And also 2D titanium carbide MXN. So today, my focus is going to be mainly on 2D titanium carbide or MXN devices. So what is MXN? So MXN is a group of material, and they are basically conductive materials that they have a element, that a element has been removed during the fabrication process. So as you can see, this is a periodic table. So max material M could be anything in this region of the periodic table. A could be any element in this region of the periodic table, and X is either carbon or nitrogen. So for the devices that I'm going to show you in this presentation, M for us is mainly titanium, and X material is carbon, and they demonstrate lots of interesting applications and performances in the microwave. So MXN has already been investigated for different purposes, especially when at lower frequencies, because they are very conductive. And due to their conductivities in their two-layer materials, they demonstrate good performance. And if I want to compare Maxine with something more tangible and feasible, I can tell you that Maxine is more like bricks, that you put sheets or bricks on top of each other and then remove the barrier layer between them and only let the valence forces to keep these two bricks attached to each other. Another example could be a sheet of or piece of paper that you can just put on top of each other, and because of the larger contact surfaces that paper to paper have with respect to each other, then definitely you have better conductivity compared to other materials. So Maxine has demonstrated electromagnetic interface shielding performance. It has been reported by so many other people in the literature, and its dielectric properties are tunable because, as I mentioned, imagine that you have bricks and material in between bricks can be changed, and by changing that material, you can change the periodicity, you can change the dielectric properties such as permittivity, or even you can introduce or reduce the loss and then tune it to your application. Same thing can happen in optical frequency ranges, and there are lots of papers that they discuss these kind of performances. But what is novel and what we did for the first time and introduce it to the world, that okay, because Maxane came as a liquid form factor, as you can see, the Maxane is inside this bottle. And because it is water soluble in its initial form factor, so you can easily just deep coat whatever device you want and make a conductive surfaces on that. So this is started by one of my former PhD students, and he started to coat some coupons. Here you can see the coupons, and we measured the conductivity at higher frequencies, and we noticed that, wow, the conductivity in high frequency, in microwave frequencies, are in an acceptable range, something maybe around 50 times less than 50, less than copper, which is still good for that frequency range. So we thought that, okay, how about we do this? How about we 3D print a waveguide, and then and now we have a plastic waveguide, as you can see here, and then deep coat the waveguide in Maxine and let it dry at room temperature. So we did that, and what I did, I also purchased exact same structure from a vendor, and definitely it was much more expensive than maybe a couple of dollars of the 3D printing that we did, but right away you can see that there is a huge difference in weight. So the weight reduced almost 10 times. So with this technique, we reduced the weight, and we noticed that the microwave, and if components can be made with this method of Maxine, it can reduce the weight and payload, which is especially important for the purpose of having satellites in the orbits. So right away we start to think, okay, what frequency bands we can make this kind of structure? What type of structure we can make? And we investigated different structures, such as you can see in figure A, like a filter, like a resonator. Another structure in figure C, it's twist, which means E field is coming perpendicular and then goes out horizontal. Also, you can see we investigate bends. And we not only just did the measurements, but also we went back, and based on the measured data, we tried to match it with the simulation and basically back extract the conductivity of the Maxine at different frequency spans. So here you can see the different fabricated structures from X band to K and Ka band and Ku band in here. So X band is from 8.2 to 12.4 gigahertz, Ku band from 12.4 to 18 gigahertz, and Ka band from 22 to 33 gigahertz range. So as you can see, we always compare it with the metal, and the result is very close. They are very comparable. And at the same time, even here you can see that some of these results at that time was repeated 3 months after the fabrication, and the degradation of the material is not something significant, and it's very negligible. Then the question came forward when we were submitting this paper, and always I also appreciate good reviewers, because good reviewers can give you a direction for research. So they asked us, okay, how much power handling this device can have? And then we investigated the power handling properties from let's say 20 dBm up to 40 dBm, which is required for the purpose of communication at that for the LEO satellites. And as you can see, changing the power is a little bit changing the transmission coefficients, but it's not significant again. And the reason that I'm saying that it's not significant, because as you can see, S21 is in the range of 0.3, 0.3, and the difference is on the third digit, which can be easily related to the accuracy of the device and vector network analyzer for the measurement. So here is the example that you see. So this is the filter that we designed. As you can see, there are some irises. And I just want to mention, if you want to make this device using metal, first of all, we cannot do it in one shot. We need to cut it half and then do machining and everything. But this device was 3D printed once, and everything is connected, and we don't need to use screws or anything like that. This is a one single time 3D printed structure, and after 3D printing, we deep coat it in the vaccine, and then that is the device that we have. Then question came forward and asking, okay, what would be the humidity stability or temperature stability of this device? So we investigated the humidity, as you can see here. So we put this device in a humidity chamber that we made in our lab. Here you can see this is a sealed chamber. There are mass flow controllers and vector network analyzers in my lab. And then we changed the humidity level in this box from 0 to almost 80%, and we monitor the humidity variation using the device that we have. So this is expected, because the vaccine is a material. It's not like a metal that it should be insensitive. So we see some changes and sensitivity to humidity. But imagine, as an example, looking into the frequency, the change is maybe around 2 megahertz at 14 gigahertz range, which is almost negligible. We also investigated, because we have different Maxen and Maxen flakes, so we also investigated the impact of different Maxen sizes or Maxen flake sizes, from a small size, which they are like an island close to each other, and large sizes, which it seems that they are larger islands getting close to each other. And as you can see, we got our very good results when we used large Maxen size for the purpose of conductivity. But small Maxen sizes also demonstrated some sensitivity when we are doing gas sensing and humidity sensing. So based on your application, based on the applications that we have, we should really tune this material to get the best results. Here is a comparison table, Maxen versus other materials, and according to our measurements, so far the Maxen method or TI3C2TX material waveguide overcome to lots of the previously reported materials, such as graphene itself, CNTs, PEDOT-PSS, conductive polymers, and so on. And one of the things that I also want to again emphasize, this method doesn't need any rigorous curing method or preparation method or anything like that. We just 3D printed the waveguide, then clean it, and then deep coat it and let it dry for 24 hours, and then it's boom, ready to use. So if you are interested about the work that I presented here and you want to see more details on the analysis and so, this is the QR code that takes you to the paper that was published in one of the well-represented journals. I think it was published in Materials Today with very, very high impact. So next student come forward, and I like this because one student do their part and then transfer their efforts to the next student. So the next student doesn't need to go back and then do everything from scratch. And I believe we need to establish this sort of culture all around the world for the purpose of pushing the science forward. So what happened is the student came forward and said, okay, you investigated waveguides, but I wanted to see if we can get the same results using antennas. So the next PhD student, she started with the designing antennas, and she started using different filaments to make sure that we get similar responses over different filaments. And here you can see she made antennas and put two Maxine antennas in front of each other at 40 centimeter. And also she investigated different distances. And here is the way that she made the antenna. What we did, we purchased exact same antennas for the purpose of comparison to see how Maxine can operate in compare to other method or in compare to commercially available device. So here are the comparison. So first we put two waveguides with no antennas at 40 centimeter distance from each other. So as you can see, when there is no antenna, definitely we are not expecting any gain. So S21 was in the level of -32. Then we install one Maxine antenna on one side, and we notice a significant increase in the gain and in the level of the S21. And we put another antenna on the other side and another maybe 10 dB gain. So adding these numbers to each other and taking average of that, we notice that this is very similar to commercially available antennas characteristics that was reported. So here you can see some comparisons. I really want to play this video to show you how fabrication could be simple. So this is a Maxine liquid or water solution, or Maxine in a water. So this is a 3D printed structure. And that's it. As simple as that. That is the entire fabrication process. So we thought, okay, since we can do that, can we also do the similar kind of structures on other electromagnetic devices? We noticed that we can also put Maxine on planar structures. And when you put on a planar structures, you can make different devices such as disc resonators over here, and something like a kirigami structure. So in the kirigami structure, kirigamis are basically structures that when you apply force, you can change the shape, and when you release the force, it goes back to its initial location. So here you can see we made SRRs, split ring resonators, and here is the interrogator antenna with the distance from the SRR. So what we did, we noticed that when we are sending a wave, if we change the distance, or if we apply force or strain to the, or stretch basically to the structure, so the wave reflects at different places, so we get different reflection. Based on different reflection, we can correlate that to the amount of the stretch that we are applying to the structure. So again, this work was well respected, and we published it in Nature Communication, and it can be used for the purpose of passive sensing of stretch in soft robotics applications. We didn't stop there. We thought that, okay, if we can do lots of, this is like a new material, we can use it for the purpose of radiation. So can we do further? Can we do something like a RFID structure? And here you can see that we have RFID structure. And actually what we did, we take a paper, a piece of paper, this is basically a regular paper, and then put some super hydrophobic coating on the parts that we don't want. And for the traces that we want, we want to coat with Maxine, we just leave it as is, no super hydrophobicity. So what is a super hydrophobic material? So super hydrophobic material, it's also called never wet. Sometimes in our houses, if you don't want, especially on the roof, if you don't want the water to stick there, there is a very simple coatings that you can purchase from a local store and just spray on the surface, and that changes the surface energy. And when you have a change on the surface energy, if you have a droplet, something like this over here, the droplet wouldn't spread. It stays as a sphere, and it can easily get off from the surface and doesn't wet the surface. But if we have hydrophilic surface, as you can see over here, the droplet wants to spread and stick itself to the surface. So by just doing this, look what can happen. And that one is the liquid or Maxine liquid on the background. This is a paper coated with the never wet. Done. The fabrication of antenna could be as simple as this. So after fabrication, it's now time for characterization and calibration. So we added some commercially available RFID chips. We had antenna on the ceiling over here, as you can see, and then we put the RFID tags that we made on the table. The distance is around 145 centimeter, which is acceptable for low power backscattered based RFID structures. And as you can see, here are the tau values that we extracted for different carrier substrate, and these are the results. And basically RFID could identify the chip in this distance. We thought maybe we can go further and then develop even something different, such as frequency selective surfaces with this method. So here, one of the same student, she made another structure she first did the simulations and then made the structure. It's called FSS. So here are the simulation for the, and FSSs are basically a repetitive structure of a microwave element, and then you have an antenna. And as you can see, this antenna here, we got a deep notch on the S parameter or S11 parameter. And as we, let's say, introduce heat, we notice that here you can see, we notice that by changing the heat or heating the surface, this notch start to move, and basically we can correlate the variation in the frequency to the variation of the temperature. And this is a very interesting and simple passive temperature sensor for heterogeneous surfaces. So with that, I would like to acknowledge all the supporters of this work and all the people and the companies and the government bodies that support our research. Here are the people work on this topic. Basically, whatever I presented is an outcome of these two students, very high caliber and knowledgeable students. Omid over here, he started with the waveguide structures. Now he has joined the ANSYS, or formerly ANSYS, now Synopsys. And now Zara, my PhD student, is working on the antenna side, and we are expecting to have some new publications in maybe next couple of weeks. At the end, I would like to again thank you for attending this talk. Thank you for paying attention and your enthusiasm. Here are the link to my lab and to the MTTS Society Distinguished Microwave Lecturers to learn more about them and see what they are doing. And finally, I would like to say that this is the lab that I have established at the University of British Columbia. We call it the Omega Lab. We correlate that to a Smith chart, which we get the students with the potential, help them to get to their success. Thank you.
Thank you so much, Dr. Zarifi, sir, for that truly enlightening talk. I'm sure the students were really intrigued as it opened a whole new world of research for them. Now, we will be taking a few questions from the audience. You're all requested to put your queries in the Q&A section, and we will be taking them one by one.
Okay, sir. Thank you very much for such nice presentations and the new dimensions that you have shown regarding the development of microwave devices. Mostly that you have mentioned the waveguide and other antenna and also some planar materials. So one question from my side, are you also doing work on antenna domain? Okay. So how we could prepare the Maxent solution at here in our lab? So in our chemical, it is related to the chemical process. So how we could...
Thank you very much. Very interesting question. So basically, I'm also a microwave and microelectronic person, not a material person. So what we do, we have a very close collaboration, okay, with different universities or with the group that they are doing materials. But also I can mention that there are some companies right now, I believe the name is Maxent Dynamics, that I believe even they are started to somehow providing material like Maxent material, or even providing these kind of waveguide, Maxent-based waveguide. They are working closely with my lab in UBC. There are also other companies such as Maxent Inc. in US that they are selling these materials. But what I can say is I mainly either purchase this material or get it from my collaborator. So, and material, after it's ready for coating, it is environmentally safe, and you just need to take a regular precautions. So it's not something like an acid or something that you need to be very, very careful.
Okay, thank you, sir. And as you mentioned that you have shown one AI chip, and which is used for edge computing devices. Yep. So I suppose that so this kind of technology will be very much useful for the IoT that we are talking about nowadays.
Absolutely, absolutely. I can a little bit elaborate on that. So basically, we are moving towards so 5G is there, and now we are planning to move to the 6G by 2030. So in 6G, we are expecting to have 10 million IoT components per kilometer square. So this is the promise. So now we need to think about a couple of things. One, how we are going to connect them. Two, how we are going to analyze them. Three, who is going to take care of the waste? Yes. And that's why we need to look into the new materials.
Yeah. One question from our audience, also a teacher, that is Maxent material is effective in airport security scanning.
Can you repeat the question, please?
Is Maxent material is effective in airport security scanning?
At this moment, I'm not sure about that, but I know Maxent is being used in so many other devices, but mainly for low frequency because they demonstrate a very good conductivity at low frequencies. But one thing that I know, this method of, not Maxent, but this method of screening, like using antennas and terahertz, yes, they are active in airport securities. I think even just a couple of years ago, they announced that in Toronto Pearson, they are using this method for monitoring in Canada, and I'm pretty sure that they are using the similar methods in other airplane and security places.
Okay, one question the general microstrip antenna. I am doing work in microstrip antenna, and a lot of people research over there. So, is the total structure of the microstrip antenna can be possible using the Maxen?
Oh yeah, absolutely. So basically, microstrip antennas are kind of similar, I'm just trying to use the words properly. So kind of similar to this one that we have here. So basically, let me see if I can stop this. Okay. So basically, can you see my mouse? This one is an RFID antenna or dipole antenna with no ground underneath with T-match structure. So if you can make something like this, definitely you can make patch antennas or other microstrip-based antennas.
Yeah. So this could be some research dimension for using the Maxen materials.
Absolutely, absolutely. What I'm saying is, I am the person just open the box.
Yes.
But whatever other people can do, I would say it's unlimited on this area for now, at least.
And one of the most advantages is very lightweight, which is useful for handheld devices and for satellite communications also.
Absolutely, absolutely, and that's why lots of satellite communication and the companies who are interested, plus big players like airplane manufacturers are also contacted us for possible collaboration and also implementation and usage.
Okay, so any more questions from the audience? Okay, so sir, mostly today's audience are undergraduate students. They are on that's either second year or third year. So just studying the antennas and microwave devices in this semester itself, I'm taking the class. I know. So they have gotten a little bit idea, as you have discussed, that about horn antenna, and they are using that in the lab. The waveguide you have shown, rectangular waveguide. I hope they have got some interest in this field, and hopefully they will come forward to research in this domain.
Absolutely, maybe something that I can tell, because I also teach electromagnetics and RF and microwave circuits at University of British Columbia. So one thing that I can tell, my second year or third year students, unfortunately, right away, they get exposed to lots of math. And then they said, oh my goodness, how I'm going to use this math for the purpose of communication. So how divergence or curl is going to help me to do these kind of things. But when I show these kind of slide first and tell them that, look, those are fundamentals for understanding what we can do, and this is finally what we are doing, then they notice that, okay, they should a little bit accept that hardship in the beginning, and then they can open themselves to lots of opportunities like this. And to be honest, I would highly recommend students to consider studying both electromagnetics and circuits, because these days circuits and electromagnetics are becoming very integrated. Previously, they said that, okay, if you study circuits, you don't need to know electromagnetic. And if you know electromagnetic, you don't need to know circuit. But now, imagine all these digital communications. It's digital, it's a gate, but everything is operating at 200 or 20 gigahertz, 1 gigahertz, 300 megahertz. These are all microwave frequency bands. So you need to take care of crosstalk, you need to take care of leakage, you need to take care of coupling. So that means you need to understand the concept for the electromagnetics.
Yes, true. Definitely, that understanding of the concept is important. some participants, Oyon Pahari is may I want to ask you something. Oyon, you can unmute yourself and ask a question. No problem. Any more questions? I can check. One question is from one student, that why do we prefer titanium? How does the changing of the elements affect the properties of the resulting maxim?
Oh, that's an excellent question. Thanks a lot for this question. So basically, by changing the material, you can change the sensitivity of the MXN layer to different components. As an example, I know that if you use vanadium, then vanadium carbide instead of titanium carbide. So then, or add at least vanadium to some place in titanium, vanadium carbide, something like that, based on the different combinations. You can make this MXN surface more sensitive to the thermal variations. So as an example, if you want to make a temperature sensor, it's better to use that type of decoration or that type of material. There are other combinations such as titanium carbide with fluorine ending, which is fluor as a attaching finishing to the surface, or maybe OH, oxygen hydroxide to the surfaces. They are more sensitive to, let's say, humidity. So it depends on the application. So we noticed that we get maximum conductivity with this particular type of the MXN. So that's the reason we selected. So at this moment, the main selection criteria is the highest conductivity, which is important for microwave communication.
Okay, sir. Ritik, sir, you may have some questions. You can unmute yourself.
Sir, good evening and good morning, sir. Sir, actually, my question is that this microwave engineering or microwave researches, how it is related with the companies, how the students will be students can get benefited, and they can join to any companies or startups, or how the things are growing or in this area, in these fields.
Okay, perfect.
In overall the world, in Canada, in perspective of India, I'm asking, sir.
Okay, so I need to come to this slide then. So that is, okay, so that question, I can start talking for hours and even complain, and I'm telling you why I'm saying this. So I always try to talk based on references. So if you go to this is my lab website. So if you go to my lab website and you can look into the people, and if you browse down, you see most, or I would say all of my students are now in well-respected companies, okay? And the reason is they are, if you work in these kind of areas, you are working in multidisciplinary or cross-disciplinary areas, and then you gain these cross-disciplinary knowledge. So that means you can relate microwave to material, to circuit, to communication, and so on. So with respect to finding job, why I said that I can complain, because most of the time I couldn't keep my student as my postdocs or my if master's student continue as a PhD, because even before they finish, they are being hired by the companies. So I would say the future is very bright for microwave and material, or microwave and circuit engineers.
Thank you, sir.
Thank you, sir.
So
Absolutely.
anybody have any questions further? Oyon, do you want to ask any questions, please? Yeah. Your voice is very low. Change your mic, probably it will help. Okay. So before, hello.
Yeah, I can hear you.
Yeah. No, I'm asking Oyon. He's a student. Might be some issues from his device.
Oh,
Anyway, thank you, sir, for your valuable time and wonderful presentations regarding the recent advancement of the microwave theory and technology. On behalf of our institute, on behalf of the MTTS Society SBC, I'd like to thank you uh, on the bottom of my heart, and hopefully we'll meet soon. Maybe I can go to the MapCon, and there also I can meet with you. Okay. And also further in near future also we are going to organize some conferences or workshops. At the time we'd like to invite you for presenting such wonderful talk regarding this recent advancements over your research area.
absolutely. And thank you so much for inviting me, and thank you everyone for attending this session and listening to their presentations.
Yeah.
You have a
Arohini,
comment?
Arohini, just conclude.
Okay, sir. So as we are concluding today's session, I would once again like to extend our heartfelt thanks to Dr. Zarifi for sharing his expertise and valuable insights with us. And also a big thank you for all the participants and faculty members for joining us. And before I conclude, I would also like to take a moment to encourage all of the participants to stay engaged with the IEEE MTT-S SBC at HIT, and warmly invite you all to be a part of the upcoming activities as well and contribute to making our community even stronger. So on that note, sir, I would like to conclude. Thank you so much once again, sir.
Thank you, Aruni. Thank you, everyone, and you have a wonderful evening.
Yes, sir.
Thank you, sir.
Wonderful
Thank
day
you, sir.
ahead of you.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.